So any force, it doesn't have to be gravity, any force that when you calculate the work done by that force, following whatever path you want, connecting I and F, if the work done by that force is independent of what path you chose, then you call that force a conservative force. And that force has some very nice property, which is that the work done between I and F is path independent. It only depends on your final point and your initial point, and more, that the work done by that force can be written as the negative of some change in some function. That function is called the potential energy associated with that force. Okay? So for the force being gravity, we concluded that the work done by gravity when going from I to F was the negative of the change in the potential energy. But if the force had been a spring, suppose that I connect the particle by a spring to this corner, and I move this particle along this path, right? And I calculate the work done by the force of the spring when I go from here to here, right? That could be a very complicated calculation, integration. When you do that calculation, if you end up with, which you will for the case of a spring, if you end up with a work that is independent of how you got here from here, then you say there must be a number, a potential energy function associated with that force, the spring, in which satisfies that to know the work of that force, I only need to know by how much did this function, potential energy, change. All I need is the initial and the final points. Okay? So conservative forces always have a function called potential energy that can tell you how much is the work done by those forces. So a force that is conservative has a potential energy function. Now, if all the forces that are acting on a system, this block, if all of them were conservative, right? If all of those forces had an associated potential energy function, then when we use the work kinetic energy theorem that says that the net work done by all of those forces should be equal to the change in the kinetic energy of the object, when we use that theorem, well, we'll break it up into the pieces that correspond to each force. This will be the work done by force 1, the work done by force 2, and so on, right? But if those forces are conservative, then there's something else I can do here. I can replace the work done by those forces by the change in the potential energy associated with them. We just said that, right? That if the force was conservative, the work done is always the negative of the change in the potential energy. So I can replace the work done by force number 1, moving from some initial to some final point. I can replace it with the negative of the change in the potential energy associated with that force. The same for force number 2, force number 3, all of them, if they're all conservative, then I can do it for all of them. And that equation can be written, of course, as delta K plus delta U1 plus delta U2 plus delta UN equals 0. So what does this equation say? The change in kinetic energy plus the changing potential 1 plus the changing potential energy 2 plus the changing potential energy 3 and so on is equal to 0. That equation implies that energy is conserved. If we call the energy of the object, if we call it kinetic plus all of the potential energies, what this equation is saying, that's the mechanical energy, kinetic plus potentials. What this equation is saying is that if all the forces are conservative, your change in mechanical energy will be 0. That's what it says. Your change in mechanical energy will be 0 if all of the forces are conservative. So if one force had been gravity and the other one had been a spring, then this statement says that take the kinetic energy plus the gravitational potential plus the elastic potential, that is your mechanical energy, that will be conserved if those are the only forces acting on the system, right? Like the block falling down, compressing the spring situation that we discussed in class, right? That will be an example of that. The forces acting on that block are gravity, which is conservative, spring force, which is conservative. So we can use conservation of energy if we use kinetic plus gravitational potential plus elastic potential. That's exactly what we did. We said the energy before was the same as the energy after. We were talking about the mechanical energy. the sum of kinetic plus potentials. Now here is a direct connection between force and of a conservative force and the potential associated with it. So what I'm starting here, the discussion is to say the work done by a force, conservative force, that was acting on between the initial location and the final location, that work would be done by the integral, or be calculated by the integral. But now I'm going to say if the 2 points are very close together, if F and I are very close, I can assume that the force was constant during that small amount of distance, right? If it's not constant, just make it smaller, right? So if the distance is very small, if your delta S is small, I can approximate this by saying that is the dot product between the force at that location, dot product with delta S. So this is the component of the force that goes along the direction S, right? If delta S had been in the x-axis, I would end up with F sub x. If delta S had been in the y direction, the dot product of F and something that goes in the y direction will be Fy times delta y, right? So that's why I put this S here. So the work done by that force, since it's conservative, should be the negative of the change in potential. And that work is equal to this product from the definition of work. But the potential, the conservative part, is showing up here by saying that this should also be equal to this. There is a potential energy associated with that force. So from that, I can say that the force, the component of the force, of that conservative force along the direction S, should be approximately equal to the negative of the change in the potential energy divided by the change by the distance along that direction. So if I evaluate the potential energy here and I get a number, and I evaluate the potential energy here, I take the difference, right? I divide it by delta S with a minus sign. That would tell me what's the component of the force along that direction. That will give me the component of the force along that direction. And in the limit, when the distance is infinitesimal, this ratio turns into a derivative, right? So this equation tells you that the component of the force, conservative force, in the S direction, x, y, or something in between, should be the negative of the derivative of the potential with respect to that direction. So another way to say what I just said is that F points always in the direction in which the associated potential energy decreases. F points in the direction in which the associated potential energy decreases. If the U ds is negative, meaning U is decreasing, F is positive. So that's the direction in which F is going to point. Let me show you that with the spring case. The potential energy of a spring is like this, right? It's 1/2 of K times x squared. That's the potential energy, a parabola. So if I evaluate here the derivative, du dx, okay, what do I get? I will get some positive number, right? The slope, du dx, at this location is positive. So what does that tell me about the force? The force is the negative of the slope, right? The equation that I just wrote was minus du dx. So since at that location the slope is positive, what direction has the force? Negative, to the left. So when you stretch this spring and you put the particle here, you let go of it, the force of the spring is to the left. That is connected to the fact that the potential energy is increasing. The force points in the direction of decreasing potential energy. The force points in the direction of decreasing potential energy. That's towards the equilibrium point. If you do it on the other side, then what would happen? On this side, the slope of the potential is negative. Negative of the slope is a positive number. On this side, the force points to the right. Okay? So the force is always pointing in the direction in which the potential energy goes down. Okay? Just like a particle sliding down a hill, right? It goes in what direction? In the direction of the decreasing potential energy. Okay? That's the force, the direction of the force. So that's what that equation is saying. For the case of the spring, notice that the connection between the force of the spring and the potential energy of the spring is given by the equation minus du dx, because the spring is a conservative force. This is true for a conservative force. So if you replace that the potential energy of the spring is 1/2 of kx squared, then just take the negative of the derivative. Derivative of that is 1/2 of k times 2x. 2 and 2 cancel, and with a minus you get minus kx. That's the force. That's how the force depends on the position for a spring. That is connected to the kinetic energy being 1/2 of kx squared, right? For the force of gravity, you can do that in your head. The force of gravity is the negative of the potential energy of gravity. What's the potential energy function? mgh. So if you take the derivative with respect to h, which is the variable that is changing, you get mg. And with the minus, you get that the force is minus mg, so downwards. The potential grows this way, the force is in the opposite direction. The force points in the direction of decreasing potential energy. For gravity, that's pretty clear, right? In a potential energy diagram, we mentioned this before, there is points that are equilibrium. So at this point, we have an equilibrium point, right? Because if the particle is displaced by a small amount away from the equilibrium, what it tries to do is go back to it, right? Doesn't go far. That's the basic idea. So this is an equilibrium point that is stable because the particle just stays there around that point. Okay? If it loses, if there is some sort of friction in this system, the particle will lose energy until it settles at the bottom of the well. So it's always going to be found there. That's called a stable equilibrium point. There's another equilibrium point, stable, at this bottom of this well, right? The same thing will happen here. Particle will not deviate too much from the equilibrium point if there is any perturbation. But there is another equilibrium point. Again, use the analogy of the landscape. I can put a ball on the top of this hill, and it's not very stable, but I could put it there and keep the ball for a little while. But eventually the ball is going to roll one way or the other because there's perturbations always happening. A little bit of wind, a little bit of ground shaking, and the ball goes one way or the other. So that's a equilibrium point, but it's an unstable equilibrium point. So now we see why we call these equilibrium points. What's the force due to that potential? What's the force at this location? It's 0 because the force is the negative of the slope of that potential of that graph. And the slope is 0 at the bottom because it's a minimum. Another place where the slope is 0 is at a maximum. That's another point of equilibrium. So equilibrium, equilibrium, equilibrium. But only these two are stable. That one is unstable.